Okay, so now that we've defined what heuristics are, let's dive in and take a look at what they do. So first, I want to talk to you about the representativeness heuristic. And for this, I would like you to pause the video and take part in a tiny demo experiment where I have added the link to this video here. So if you've taken part in this representativeness heuristic demonstration experiment, you'll see that I have asked you which sequence of numbers in a lottery is more probable. The upper sequence reads 23, 84, 13, 45, 39, and 6. And the lower one reads 1, 2, 3, 4, 5, 6. Now, of course, actually, both sequences are equally likely, since these numbers are randomly drawn. But many people, and perhaps even you, will think that the former sequence, the one that starts with 23, is actually more likely to occur than the one that's perfectly ordered. And why is that? Well, representativeness heuristics, or from the perspective of representativeness heuristics, we would argue that the 23, 84, 13, and so on sequence, it just looks more like a sequence of random numbers, right? And 1, 2, 3, 4, 5 doesn't look like a typical sequence of random numbers. And yeah, so because of this idea that something is more representative for its category, that's where we would get this kind of distortion in judgments from. Now, in the link to the experiment, you should also be able to see in the end the results, not only of yourself, but also of other people who've participated in this. And it will be interesting to see if indeed it is the case that more people think that 23, 84, and so on is a more likely sequence in a lottery than 1, 2, 3, 4, 5. Because if that wasn't the case, then we should have about a 50-50 split between these two. Okay, so that means a representativeness heuristic basically is based on the idea of asking how typical is a certain element for its specific category. So in our example with the lottery, how typical is the sequence for the category of sequences of random numbers? In another way of phrasing this is, how well does a specific case represent an abstract model? So how well does our sequence of numbers represent our abstract model of what random number sequences look like? Representativeness is one of the heuristics that we use as a basis for categorization and probability judgments. And here the idea is that the more prototypical the specific case is for the model, the greater we believe the probability is that the case belongs to the model. So the more our sequence looks like a random sequence, because it just fits better to how we believe random sequences should look like, the more likely we will think it actually fits to that category. Yeah, and then also the greater the likelihood that our specific case will be assigned to the category. So I would like to give you another example for a representativeness heuristic, now that we've discussed the idea of random numbers and looking representative for a random sequence. And again, I'd like to ask you to participate in a small experiment, and this time we need 2 groups. So I'm going to have to ask you to flip a coin again. And if you're heads, please answer the questionnaire that I link here for the heads group. And if you got tails and the coin flip, please answer the questionnaire for tails. That's also linked here. All right. So if you've taken a look at this experiment, you will see that this is basically the task that I put. So in one group, that's the heads group, Tamara is described as married. She has 2 children. She's 34 years old and highly skilled and motivated in her job. And in the other, that would be the tails group, the same person, Tamara, is described as married, having 2 children, 34 years old, highly skilled and motivated in her job. And we have one additional piece of information about her, which is that she flies an airplane in her free time. Now, we are in both cases supposed to judge what the probability is that Tamara is an engineer. And in addition, we also know that Tamara is a member of a group of 10 people. And in this group of 10 people, 7 of them are lawyers and 3 of them are engineers. Now, if there was no such thing as a representativeness heuristic, we would expect that basically there should be something like a 30-70 distribution in our estimates of whether Tamara is an engineer, right? Because the base rate says that 30% of our group of 10 people are engineers. But in the case where there's additional information about her, which is that she flies airplanes in her free time, actually what we see is that many people will ignore the base rate and they will not say, well, there's a 30% probability that Tamara is an engineer. But people will overestimate that probability because someone who flies an airplane in their free time fits better in the category of being an engineer. So it's more sort of stereotypical or prototypical or representative of the category of engineers. So to phrase this differently, Tamara's representativeness has predictive value for people, but so does the base rate, right? Representativeness is relatively to base rate often overestimated in terms of the value that people predict. So in the case of Tamara, if you compare the answers that people give in our 2 questionnaires, so the one where there is information about her flying airplanes in her free time, and there is no such information, we should see that there is actually a difference, and the probability that people in the airplane condition estimate that Tamara is an engineer should be higher than that in the other condition where we don't have the airplane information. Okay, here's another example of representativeness heuristics. So not only base rates are often ignored, and then, or we could also call this a base rate fallacy, by the way, but also sample sizes. And ignoring sample sizes is sort of, we can file that under the idea of representativeness. So in this task, people were asked to estimate the percentage of female babies born in hospitals of different sizes. So you can see hospitals are here split by whether they have about 10 births per day, 100 births per day, or 1,000 births per day. So 10 being in black bars and 100 being in white bars. And then the percentage of female babies in expectation should be around about 50%, right? And you can see here we have a distribution. Some people will say, well, female babies happen all the time, so between 95 and 100% of the time. And some people will say the majority, many people will say there's a 50-50 chance-ish of a female baby being born. And the important bit here is that we can't see a lot of difference in people's estimates of the probability of a female baby being born in hospitals of different sizes. We can't see that vary by the number of births per day. Now, if we compare this estimate where the black, gray, and white bars are kind of always at the same height for each of the categories of probabilities, we can take this and we can compare it with the actual percentage of female babies born in hospitals of different sizes. And you can see here that there is a huge spike of this probability in the case where there are actually lots of births in that hospital. Now, why is that the case? It's the case because the law of large numbers indicates that as sample size increases, so between 10 and 1,000 babies, the sample statistics become less variable and should more closely estimate their corresponding population parameters. So if we have a tiny hospital with only 10 births per day, the chance that there's like a fluke and all of these babies will be female in one day is actually higher than if we have a hospital with a lot of births, let's say 1,000 in a single day. And the probability that there we significantly deviate from the actual underlying probability of female babies being born, which is somewhere around 50%. In these huge hospitals, a deviation from these 50% is just far more unlikely. But as you can see, if we again compare, people are really not good at estimating this correctly. People tend to think that sample size doesn't matter for their estimates. While in truth, it should. Now, what does this have to do with the representativeness heuristic? Well, it seems odd that this should be the case, that there should be a spike depending on the size of the hospital, right? So this is not in our concept of random distributions, and therefore we make these errors in judgment. I can show you another example of a fallacy in this case that's related to representativeness, which is called the hot hand phenomenon. So if you're a sports fan, you might know about this. This is the belief that a player who just scored twice or 3 times in a row is more likely to score again. And here I have some data from Gilovich et al., where 100 basketball fans were asked, and almost all of them believe that the probability for scoring another hit increases after some more hits. And again, a huge majority believe that it's important to pass the ball to someone who just made several hits because they're on a roll. They have a hot hand. But of course, one hit and another should probably be treated as random events. Now, in basketball, if you argue that there's some skill involved, there might be some reason why the hot hand phenomenon makes some sense, right? Because someone who just scored, probably they're a good player and they might be more likely to score again. But still, if we assume that all of them have kind of a similar skill, then we should be back to the idea that basically these are random events. Now, we can take a look at some actual data, looking at the probability of making a shot, so of scoring a point, conditioned on the outcome of previous shots. And again, this is still from the same study. So here are 9 members of the baseball team, the 76ers. And for them, now here we have the probability of making a shot, so P of X, given either they made a shot before, so that would be given X, or that they didn't make the shot before, that would be a 0. So the first column then would be the probability of making a shot, given that the player had just before missed 3 times in a row. And the second column would be the probability of making a shot, given that the player had just before missed 2 times in a row. And then this way, again, we have this for the probability that a player would make a shot, given that they had just made a shot, or had made 2 shots, or had made 3 shots, right? And if you take a look at the last column, you will see that this is the correlation between the outcomes of consecutive shots, and there's just no deviation from 0. So there is actually no evidence that the hot hand phenomenon exists in this case. And in contrast, if at all, it might be rather the case that hits are more likely after misses. So if someone just didn't score a lot of points, and then they finally get another chance, they might pour all of their skill and all of their resources into making that shot, and that might give them a bit of an advantage, right? But the gambler's fallacy here is again an example of the representativeness heuristic, because the idea is that someone who, in our minds, basically someone who's just scored a shot is more representative of the category of people who will score shots, and therefore we assign a higher probability to them scoring yet another shot. An example of the representativeness heuristic. In this case, the conjunction fallacy. Imagine that I introduce you to a person. This is Junhui. And Junhui likes computers and she doesn't like boys. That's what you know about her. Now, if I ask you, what is the probability that Junhui studies computer science and the probability that she studies computer science and likes anime? People make a very specific error in how they judge these 2 probabilities. The logic, of course, should be that the probability of 2 independent events co-occurring cannot be higher than the probability of each independent event on its own. So let's say the probability that Junhui studies computer science is 0.3, 30% probability. the probability that she likes anime is, let's say, 0.15, whatever. So that would mean that the probability that she studies computer science and that she likes anime is the product of her, the probability of her studying computer science and the probability of her liking anime. So it would be 0.3 times 0.15, and that would make 0.045. So that means it is far less likely that both is true than that each individual event is true, right? However, people will think that the probability that Junhui studies computer science is smaller than that she studies computer science and likes anime. So they make an error in conjoining independently occurring events. And this would be an example of the representativeness heuristic because, well, why do people make this error? Because they believe that, because we people, some believe that it is that Junhui studying computer science and liking anime it makes her more representative, that feels like more stereotypical of this Asian girl who doesn't like boys and likes computers, as described in this tiny short description. It makes her more representative of the category, and therefore the probability assigned to this option is judged to be higher. Right? So of course this is a terribly stereotyped view, but it seems like we make these cognitive errors, and in this case, the probability that two independent events co-occur is just misjudged because of how representative this makes Junhui for her category, even though that's not how it logically should be done. Okay, so now that means we've seen a bunch of examples of representativeness heuristics in action. And the idea always is that because an object is more or less representative for its category, it will be judged differently.